Picture for a moment the crushing weight of an entire mountain pressing down on a single grain of sand. That's the kind of force we're dealing with when we talk about the universe's most extreme pressures, a realm where matter behaves in ways that defy everything we know. Out there in the vast, silent darkness of space, celestial bodies wield forces so immense they twist the very fabric of reality. Today, we're diving into the heart of these cosmic extremes, where gravity doesn't just bend rules, it shatters them. Think about a neutron star, a stellar remnant so dense that a single teaspoon of its material would weigh billions of tons here on Earth. These cosmic powerhouses are born from the explosive deaths of massive stars, collapsing under their own gravity until atoms themselves surrender, squeezing protons and electrons into a sea of neutrons. But even that pales in comparison to the ultimate pressure chambers of the universe, black holes. Here, gravity becomes so overpowering that not even light can escape its grip, warping space and time into a singularity where our understanding of physics simply breaks down. What makes these extremes so fascinating isn't just their sheer force, it's how they challenge everything we think we know. From the crushing cores of giant planets to the violent collisions of distant galaxies, these pressures sculpt the universe in ways that seem almost supernatural. And yet, they're real, measurable, and happening right now across the cosmos. So buckle up because we're about to explore 30 of the most mind-bending, awe-inspiring examples of cosmic pressure, each one revealing just how strange and magnificent our universe truly is. This isn't just science, it's a front-row seat to the universe's most spectacular extremes. Let's start with one of the most extreme pressure factories in the cosmos, the neutron star. Imagine taking all the mass of our Sun and crushing it down into a sphere no wider than Manhattan. That's the reality of these cosmic anomalies, where gravity wins an endless tug of war against the very structure of matter itself. At their cores, the pressure becomes so unimaginably intense that atoms cease to exist. Protons and electrons are forced together, merging into a dense ocean of neutrons. This bizarre state, called degenerate neutron matter, defies everything we see in normal matter. If you could scoop up just a sugar cube's worth of this material, it would weigh more than Mount Everest. But the crushing density is just the beginning. Neutron stars also boast magnetic fields so powerful they make Earth seem laughably weak trillions of times more intense. These fields warp the very fabric of space around them, twisting charged particles into beams that sweep across the cosmos like interstellar lighthouses. Some neutron stars, called magnetars, take this even further. Their magnetic fields are so strong they could strip the data off every credit card on Earth from halfway across the galaxy. What's truly mind-bending is that these extreme conditions aren't just theoretical, they're happening right now, scattered throughout our galaxy. Every neutron star is a laboratory of physics pushed to its breaking point, where the rules we know on Earth bend to something far stranger. And yet, despite their unimaginable power, these cosmic titans are remarkably compact, so small you could fit one between New York and Boston. Yet with gravity so fierce, even light struggles to escape its pull. This is nature's ultimate high-pressure experiment, proving that in the vast reaches of space, even the simplest laws we take for granted can be rewritten beyond recognition. Now let's talk about the spectacular violence that gives birth to these cosmic oddities. When a massive star, think 8 times heavier than our Sun or more, reaches the end of its life, it doesn't fade quietly. Instead, it stages the universe's most dazzling farewell party, a supernova explosion. In less time than it takes to blink, the star's core collapses inward at nearly a quarter of light speed, while the outer layers rebound outward in a shockwave of unimaginable power. This single explosive event can outshine entire galaxies for weeks, releasing more energy in seconds than our Sun will produce in 10 billion years. What happens next is even more extraordinary. As the outer layers blast into space in a kaleidoscope of newly forged elements, the core keeps collapsing under its own weight. Atoms get crushed together so violently that electrons get shoved into protons, transforming them into neutrons. The pressure becomes so intense that an entire star's worth of matter gets compacted into a sphere no bigger than a city, creating the ultra-dense heart we call a neutron star. This whole process happens faster than you might think. From initial collapse to newborn neutron star takes barely 10 seconds. What makes this transformation truly mind-blowing is how it rewrites the rules of matter. Under normal circumstances, atoms are mostly empty space. If you expanded one to the size of a football stadium, the nucleus would be a mere grain of sand on the 50-yard line. But in a neutron star's core, that empty space vanishes completely. The pressure becomes so overwhelming that atomic nuclei get packed together like sardines, creating a substance denser than anything else in the known universe except for black holes. It's the ultimate cosmic alchemy, turning an entire star into a crystalline sphere of pure neutrons, with a crust harder than diamond and a gravitational pull that bends light itself. This stellar metamorphosis doesn't just create bizarre objects, it seeds the universe with the building blocks of life. The supernova's shockwave blasts heavy elements like gold, platinum, and uranium across interstellar space. Every piece of jewelry you've ever worn likely contains atoms forged in such explosions. So when we study neutron stars, we're not just exploring extreme physics, we're uncovering our own cosmic origins, written in the ashes of dead stars that died in the most violent, beautiful explosions the universe can produce. Among the neutron stars strewn across our galaxy, some reveal their presence in the most dramatic way possible by sweeping beams of radiation through space like celestial lighthouses. These are pulsars, neutron stars spinning so fast they could complete hundreds of rotations in the time it takes you to read this sentence. Their rhythmic pulses of light, radio waves, and even gamma rays aren't just cosmic quirks. They're some of the most precise clocks in the universe. Take the Crab pulsar, nestled in the remnants of a supernova witnessed by Chinese astronomers in the year 1054. This city-sized powerhouse spins 30 times every single second, flinging out twin beams of radiation with metronomic consistency. Each rotation sends a pulse our way so reliable that when scientists first detected these signals in 1967, they nicknamed them LGM1, jokingly suggesting they might be messages from little green men. The truth was almost as startling. Nature had crafted a timepiece more accurate than any atomic clock on Earth. What makes pulsars so astonishing isn't just their speed, it's the physics behind their precision. Their beams originate from jets of charged particles racing along magnetic field lines at nearly light speed, focused into narrow cones by the pulsar's immensely strong magnetic field. As the star whirls, these beams sweep across space like the spinning light on a police car, only here, the siren can be seen from thousands of light years away. But pulsars aren't just cosmic novelties, they're invaluable tools for astronomers. Their unwavering pulses allow scientists to test Einstein's theory of relativity with breathtaking accuracy, detecting subtle warps in space-time caused by gravitational waves. Some pulsars, locked in orbital dances with other stars, have even helped us indirectly confirm the existence of gravitational waves decades before LIGO made headlines. And because their spins slow down predictably over millennia, we can use them as galactic mile markers, mapping the structure of our Milky Way with pinpoint precision. Perhaps most remarkably, these spinning marvels connect us to the universe's grand timescales. The youngest pulsars, like the one in the Crab Nebula, race frenetically as they bleed energy into space. The oldest, having spun down over billions of years, tick sedately like retired clockmakers, yet all of them, whether flashing every few milliseconds or lumbering along at 1 pulse per minute, serve as reminders that even in the most extreme environments, the universe operates with a rhythm we're only beginning to understand. If neutron stars are the universe's ultimate pressure chambers, then magnetars are their most temperamental siblings, cosmic powerhouses with magnetic fields so intense they rewrite the laws of physics. Picture a magnetic force so strong it could liquefy the atoms in your body from 1,000 kilometers away, or warp the electron clouds of every molecule in its vicinity. These are not hypothetical scenarios. Magnetars exist, and their magnetic fields measure a staggering 1,000 trillion times stronger than Earth's. To put that in perspective, if a magnetar replaced our moon, its magnetic field would effortlessly strip every hard drive on Earth, scramble satellites, and turn the auroras into a global light show visible even at noon. What makes these objects so volatile are the titanic forces trapped beneath their surfaces. Unlike regular neutron stars, magnetars don't just spin, they writhe under the strain of their own magnetism, their crusts cracking like frozen lakes under pressure. These fractures, called starquakes, unleash energy equivalent to millions of nuclear bombs in milliseconds, producing gamma-ray flares so bright they briefly outshine every other source in the galaxy. In 2004, a magnetar 50,000 light-years away, so distant it should have been invisible, released a burst so powerful it temporarily ionized Earth's upper atmosphere, despite being halfway across the Milky Way. The origin of these ridiculous magnetic fields remains one of astrophysics' greatest puzzles. One theory suggests they're born from a cosmic perfect storm, when a collapsing star's core spins fast enough to create a dynamo effect, amplifying magnetic fields to impossible levels during its formation. Others propose that the violent merger of two neutron stars could twist magnetic field lines into a knotted frenzy, birthing a magnetar in the aftermath. Whatever the cause, the result is an object that behaves like nothing else in nature, a celestial monster capable of bending spacetime itself with its magnetic grip. But magnetars aren't just destroyers, they're also cosmic alchemists. Their fields are so strong they can theoretically transform empty space into a strange material called magnetic vacuum, where light itself splits into distinct polarization states. Some researchers even speculate these fields might briefly unify nature's fundamental forces, offering us a glimpse into physics conditions that haven't existed since the Big Bang. And because their outbursts are visible across intergalactic distances, magnetars serve as natural laboratories for testing quantum electrodynamics under extremes no Earth-bound experiment could ever replicate. Yet for all their fury, magnetars are fleeting phenomena. Within 10,000 years, a blink in cosmic time, their magnetic fields decay, their starquakes quiet, and they fade into obscurity as ordinary neutron stars. This makes every detected magnetar eruption a precious snapshot of the universe's most extreme magnetism in action. So when astronomers catch one flaring, it's not just a spectacle. It's a front-row seat to physics pushed beyond its breaking point, where the very fabric of reality gets stretched to its limits. At the edge of a black hole lies the ultimate cosmic boundary, the event horizon, where gravity's grip becomes so overpowering that not even light can fight its pull. Imagine standing at the top of Niagara Falls, watching water thunder over the edge. No matter how fast you paddle upstream, once you cross that brink, there's no going back. The event horizon works the same way, except instead of water, it's the fabric of spacetime itself cascading inward at speeds beyond comprehension. Here, the escape velocity, the speed needed to break free, exceeds 300,000 kilometers per second, making light itself a prisoner. This boundary isn't some solid wall or physical barrier. It's more like a one-way curtain woven from gravity's purest extremes. Cross it, and every possible path through spacetime bends relentlessly toward the black hole's center. Time distorts in ways that seem ripped from science fiction. For an outside observer, your approach would appear to slow until you're frozen in place, a ghostly smear fading into red-shifted oblivion. Yet from your perspective, if you could survive the tidal forces, you'd plunge through in moments, racing toward the singularity where known physics dissolves. What makes the event horizon so fascinating isn't just its lethality, it's how it warps our understanding of reality. General relativity predicts that space-time here curves so severely that the very concept of forward becomes meaningless. The black hole's spin can drag space around it like syrup swirling around a spoon, creating a vortex where even objects moving straight inward spiral helplessly. Some theories suggest quantum effects might transform the horizon into a seething firewall of energy, while others argue it remains smooth and uneventful, a paradox that continues to divide physicists. Yet despite their terrifying reputation, black holes aren't cosmic vacuum cleaners. Their event horizons have finite sizes, and their gravitational pull weakens with distance like any massive object. Our solar system could orbit a black hole just as safely as it does the Sun, provided we keep a respectful distance. This duality makes them both destroyers and architects. Their immense gravity can shred stars, but they also anchor galaxies, their event horizons serving as the dark hearts around which entire universes of stars may dance. The very existence of event horizons forces us to confront the limits of human knowledge. Beyond them lies a realm where time and space trade roles, where matter gets compressed to infinite density, and where the laws of physics as we know them cease to apply. They're nature's ultimate keepers of secrets, cosmic sensors guarding truths we may never fully grasp. And perhaps that's the most humbling part. In a universe full of extremes, the event horizon stands as a stark reminder that some doors once opened can never be closed again. Crossing the event horizon might seem like the ultimate point of no return, but for any object venturing too close to a black hole, the true nightmare begins long before that invisible boundary. This is where the cosmic phenomenon of spaghettification takes center stage, a gruesomely poetic process where gravitational tidal forces stretch and compress matter into oblivion. Picture a raw piece of spaghetti dangling over a pot of boiling water, slowly softening until it elongates and thins before finally snapping. Now imagine that same principle applied by gravity so intense it could turn a human, or even an entire star, into a stream of subatomic particles. The root of this violent transformation lies in the extreme difference in gravitational pull between your head and your feet as you approach the black hole. Near smaller stellar mass black holes, this gradient becomes lethally steep over incredibly short distances. If you were falling feet first toward one, the gravity at your toes could be thousands of times stronger than at your head. Your body would stretch like taffy, bones and muscles tearing apart as molecular bonds fail under the strain. Simultaneously, the sides of your body would experience crushing compression from the surrounding forces, squeezing you thinner than a pencil. Within seconds, you'd become a stream of atoms spiraling toward the event horizon, a human reduced to cosmic noodles. But not all black holes treat matter so viciously. Supermassive black holes, like the 4 million solar mass behemoth at our galaxy's center, offer a slightly less horrific fate. Their immense size spreads the tidal forces over greater distances, making the gradient far gentler. An astronaut crossing the event horizon of Sagittarius, a star, might not even notice the exact moment they passed it, at least until the inevitable spaghettification began deeper inside. The difference is like comparing jumping into a woodchipper versus slowly sinking into a tar pit. Both end badly, but one gives you marginally more time to contemplate your choices. What makes this process so fascinating to physicists isn't just its destructive spectacle, it's the window it provides into gravity's fundamental nature. Spaghettification demonstrates how gravity isn't just a force pulling objects together, but a curvature of space-time that warps everything in its path. As matter stretches, it emits detectable X-rays and gamma rays, creating luminous signatures that help astronomers locate otherwise invisible black holes. Some scientists even speculate that in rare cases, extremely rapid black hole rotation could twist stretched matter into exotic ring-shaped structures before total disintegration. The cruel irony is that this violent demise also seeds new cosmic beginnings. As spaghettified matter swirls at nearly light speed, friction heats it to millions of degrees, creating the brilliant accretion disks we observe around active black holes. These disks become stellar recycling plants, blasting newly forged elements back into space via powerful jets. So while spaghettification marks the end for whatever falls in, it simultaneously fuels the birth of future stars and planets, proving that in the universe's most extreme environments, destruction and creation are often two sides of the same coin. Some of the most violent cosmic spectacles occur when supermassive black holes wake from their slumber and begin feasting on anything unfortunate enough to wander too close. These feeding frenzies transform normally invisible gravitational monsters into the brightest objects in the universe, quasars that can outshine thousands of galaxies combined. The secret behind their staggering luminosity lies in the brutal physics of destruction. Stars, gas clouds, even smaller black holes getting torn apart by tidal forces and compressed into searing hot accretion disks spinning at nearly light speed. Take the quasar Ton 618, for example. Though over 10 billion light-years away, its brilliance makes it visible through amateur telescopes, a testament to the incredible energy released as it consumes roughly one sun's worth of material every day. As matter spirals inward, friction heats it to millions of degrees, causing it to glow across the entire electromagnetic spectrum. The process resembles water swirling down a drain, except here the drain warps spacetime itself, and the water shines with the intensity of a trillion suns. Our own galactic center offers a tamer but equally fascinating example. Sagittarius, a star, the supermassive black hole anchoring the Milky Way, typically consumes so little material that it's remarkably quiet until recently. In 2019, astronomers observed its brightness suddenly spike 75 times over just 2 hours, likely caused by a rogue gas cloud or small star venturing too close. This brief flare-up gave scientists a rare glimpse of the feeding mechanisms that power far more active black holes. What makes such events so valuable is how they reveal the chaotic environment near event horizons, where magnetic fields twist plasma into powerful jets that shoot outward for thousands of light-years. The sheer scale of these cosmic feasts defies comprehension. In brightest quasars, the accretion disks stretch wider than our entire solar system, yet concentrate enough energy to influence galaxy formation billions of light-years away. Some jets punch through intergalactic space for millions of years, creating radio lobes larger than galaxy clusters. These aren't just destructive processes, they're sculptors of cosmic architecture, regulating star formation and distributing heavy elements across the universe. Perhaps most remarkably, we're seeing these events as they occurred when the universe was young, since light from distant quasars takes billions of years to reach us. Each one serves as both a beacon from the early cosmos and a laboratory for physics under conditions impossible to recreate on Earth. So when astronomers detect a new quasar flaring to life, they're not just witnessing destruction, they're observing the universe's most extreme recycling program, where entire stars become the fuel for light that will shine across cosmic time. Even among the universe's most extreme pressures, there exists an ultimate boundary, a point where the very concept of pressure as we understand it ceases to make sense. This is the Planck pressure, nature's hard limit, where the fabric of reality itself begins to unravel. At 4.6 times 10 to the 113th pascals, it's a number so incomprehensibly large that comparing it to everyday experiences feels futile. To put it in perspective, the pressure at Earth's surface, what we feel as 1 atmosphere, is a mere 10 to the 5th pascals. The crushing core of a neutron star reaches about 10 to the 34th pascals, enough to turn atomic nuclei into a sea of neutrons. But the Planck pressure, it dwarfs even these cosmic extremes by nearly 80 orders of magnitude. This staggering threshold isn't just about scale. It represents a frontier where our current understanding of physics collapses. At this pressure, gravity becomes so intense that it rivals the other fundamental forces, creating conditions similar to those in the first moments after the Big Bang. Quantum fluctuations, normally imperceptibly tiny, would warp space-time itself into a frothing, chaotic foam. Space and time lose their smooth continuity, breaking into discrete, indivisible units at the Planck length and Planck time. Matter as we know it couldn't exist here. Instead, particles would be crushed into a state where their very identities blur into an indistinct quantum soup. What makes the Planck pressure so fascinating isn't just its extremity, but what it reveals about the limits of human knowledge. Beyond this point, our equations fail general relativity's smooth spacetime and quantum mechanics' probabilistic rules clash irreconcilably. It's a reminder that the universe operates on scales and intensities so far beyond our daily experience that even our most advanced theories can only guess at what truly happens there. Some physicists speculate that reaching Planck pressures might require energies so concentrated they'd spontaneously form microscopic black holes, while others suggest it could unveil hidden dimensions or new fundamental particles. Yet despite being theoretically unreachable even in the cores of the most massive neutron stars or during black hole collisions, the Planck pressure serves as a cosmic signpost. It marks the edge of the known, where the roadmap of physics ends and the terra incognita of quantum gravity begins. For scientists, it's both a challenge and an invitation. A challenge to develop new theories that can penetrate this extreme regime, and an invitation to imagine what wonders or terrors might lie just beyond nature's ultimate pressure barrier. To grasp the pressures of the early universe, we need to rewind time to its very first microseconds, an era so extreme it makes neutron stars look tame. Picture the cosmos squeezed into a space smaller than a single atom, hotter than the core of any star, with pressures reaching 10 to the 35th pascals. At this incomprehensible density, the universe wasn't filled with atoms or even atomic nuclei, just a seething plasma of quarks and gluons, the fundamental building blocks of matter, ricocheting at near light speed through a broth of pure energy. This was the quark-gluon plasma, nature's ultimate pressure cooker. Under ordinary circumstances today, quarks never exist alone. They are forever bound together in groups of 2 or 3 by the strong nuclear force, forming protons and neutrons. But in the Big Bang's first moments, pressure and temperature were so staggering that even this force couldn't hold them together. Quarks moved freely, like individual ingredients in a cosmic soup, rather than the combined meals we recognize as particles. Then, as the universe expanded and cooled past 10 trillion degrees in that first microsecond, something extraordinary happened. The pressure dropped just enough for quarks to snap together in threes, forming the first protons and neutrons that would later build every atom in existence. Scientists at CERN Large Hadron Collider have recreated these primordial conditions by smashing lead nuclei together at 99.9999% of light speed. These collisions, lasting less than a billionth of a second, briefly generate temperatures 250,000 times hotter than the Sun's core, temporarily liberating quarks from their bonds. Detectors surrounding the collision points capture the aftermath, showing how quarks recombine into hadrons just as they did when the universe was barely a trillionth of a second old. What makes these experiments so revolutionary isn't just their recreation of the past, it's how they reveal quirks in nature's strongest force. The quark-gluon plasma behaves less like a gas and more like a nearly perfect liquid, flowing with almost zero viscosity despite its unimaginable density. This unexpected fluidity hints at deep connections between the early universe's physics and exotic states of matter we're only beginning to understand. Even more remarkably, these collisions occasionally produce strange matter, fleeting particles containing rare, strange quarks that might exist naturally in ultra-dense neutron star cores. By studying these microscopic fireballs, physicists are essentially running the universe's first moments in reverse, watching matter dissolve into its components before reassembling, like baking a cake to examine the raw ingredients. Each collision peels back another layer of cosmic history, showing us how pressures beyond human comprehension shaped the very fabric of reality. And hidden in that data might be clues to mysteries we've yet to even imagine, like why the universe contains far more matter than antimatter, or whether even quarks have smaller ingredients waiting to be discovered. The Big Bang's first microseconds weren't just a spectacle of extreme physics, they were the crucible that forged everything we are. Among the stellar graveyard's most fascinating residents are white dwarfs, Earth-sized embers of stars that once shone like our sun. These dense cosmic diamonds form when medium-sized stars exhaust their nuclear fuel and gently shed their outer layers, leaving behind a scorching hot core about the size of Earth but packing half a sun's worth of mass. What keeps this compact remnant from collapsing further isn't nuclear fusion, but a quantum quirk called electron degeneracy pressure, a force born from electrons refusing to occupy the same quantum state, creating an invisible barrier against gravity's relentless squeeze. Consider Sirius B, the dim companion to the brightest star in Earth's night sky. This white dwarf may be smaller than our planet, but its density is staggering. A single teaspoon of its material would weigh roughly 5 tons here on Earth. That's like compressing multiple elephants into a sugar cube. Such extreme density warps space-time around it so severely that light struggling to escape loses energy, shifting toward redder wavelengths in an effect astronomers call gravitational redshift. Einstein predicted this phenomenon decades before we could observe it, making white dwarfs among the first celestial laboratories for testing his theory of general relativity. The journey to this state is just as remarkable as the object itself. Stars like our Sun spend billions of years fusing hydrogen into helium, then helium into carbon and oxygen. When fusion can no longer counterbalance gravity's pull, the star puffs away its outer layers in a glowing planetary nebula, a cosmic hourglass marking the transition from active star to dense remnant. The exposed core, initially blazing at over 100,000 degrees Celsius, begins a slow cooling process that will take trillions of years, gradually fading from white-hot to red, then finally to a cold black dwarf, a theoretical end state the universe hasn't existed long enough to produce yet. What makes white dwarfs particularly intriguing is their crystalline future. As they cool, their carbon-oxygen interiors may crystallize into structures resembling diamonds, except these gems would span thousands of kilometers. Some researchers speculate our galaxy's oldest white dwarfs could already have cores that are 50% crystal, making them the universe's largest diamonds. Yet even this pales next to their potential fate in binary systems. If a white dwarf siphons enough material from a companion star, it can reignite in a catastrophic thermonuclear explosion, the very mechanism behind Type Ia supernova that seed galaxies with heavy elements. These stellar cinders serve as both cosmic time capsules and gravitational puzzles. Their spectra reveal the precise composition of their progenitor stars' cores, while their mass-radius relationship challenges physicists' understanding of dense matter. And since 97% of all stars will eventually become white dwarfs, studying them offers a glimpse into the eventual fate of most stellar systems, including, billions of years from now, our own sun's quiet transformation into one of these incredibly dense, enduring relics of stellar evolution. Deep within the ice giants Uranus and Neptune, a dazzling cosmic phenomenon unfolds, one where methane transforms into glittering diamonds that rain through alien oceans. These distant worlds, often overshadowed by their gas giant siblings, harbor interior pressures exceeding 100,000 times Earth's atmospheric pressure, creating conditions so extreme they turn simple hydrocarbon molecules into precious gems. It's a process that sounds like science fiction, but laboratory experiments here on Earth have actually recreated fragments of this surreal alien weather. The journey begins in the upper atmospheres of these ice giants, where methane, the same gas that fuels stoves on Earth, forms thick clouds. As you descend through layers of increasingly compressed hydrogen and helium, temperatures rise dramatically while pressures mount to mind-bending levels. Around 8,000 kilometers down, where pressures surpass 700 gigapascals, something extraordinary happens to those methane molecules. The intense heat and pressure rip them apart, liberating carbon atoms from their hydrogen partners. These free carbon atoms then get squeezed into crystalline structures, raw diamonds in the making, while the leftover hydrogen gets dissolved into the surrounding supercritical fluid. But the real spectacle begins once these diamonds form. Unlike Earth, where gems remain trapped in rock, Neptune and Uranus may host entire oceans of liquid carbon hundreds of kilometers deep. Imagine diamonds, some possibly weighing millions of carats, sinking like hailstones through this strange, electrically conductive sludge. As they plunge deeper over thousands of years, friction may even melt them back into liquid before the cycle repeats in a continuous, glittering downpour. Scientists at SLAC National Accelerator Laboratory proved this wasn't just theoretical by recreating Neptune's interior conditions using high-powered lasers. When they blasted a polystyrene film similar to methane's composition with shockwaves, the carbon atoms almost instantly arranged into nanometer-sized diamonds. On the ice giants, this process likely occurs on a planetary scale, with diamond hailstones accumulating near the core in layers that could be kilometers thick. What makes this discovery so revolutionary isn't just the novelty of alien gemstones, it's how it reshapes our understanding of planetary interiors. The energy released by sinking diamonds may explain why Neptune radiates more heat than Uranus, potentially driving violent convection currents that power these worlds' bizarre magnetic fields. Some astrophysicists even speculate that over billions of years, a diamond-rich layer might have formed around the cores of these planets, creating the universe's most extravagant mantle imaginable. This revelation also forces us to reconsider what precious means in cosmic terms. On Earth, diamonds are rare because our planet's interior pressures rarely reach the necessary extremes. But on ice giants, they may be as common as raindrops, another reminder that the universe routinely transforms mundane materials into wonders under the right combination of pressure, heat, and time. So the next time you see a diamond ring, remember, somewhere in the depths of our solar system, nature is crafting jewels on a scale that would dwarf every gem ever mined on Earth. Buried beneath thousands of kilometers of rock and metal lies one of the most extreme environments in our solar system, Earth's solid inner core. This searing hot iron sphere endures pressures 3.6 million times greater than what we experience at the surface, withstanding temperatures comparable to the sun's photosphere without melting. The secret to this paradoxical state, solid metal at 5,500 degrees Celsius, lies in the extraordinary crushing force that alters iron's fundamental properties, packing its atoms into an ultra-dense crystalline structure that defies normal thermodynamic rules. Seismic waves from earthquakes have given us our clearest window into this inaccessible realm. When tremors ripple through the planet, their speed and deflection patterns reveal startling details about the core's composition. Certain types of seismic waves, called shear waves, can only travel through solids, and their detection passing through the inner core in the 1930s provided the first proof of its solid nature. More recently, sophisticated networks of seismometers have detected waves slowing dramatically as they enter the inner core, suggesting its structure isn't uniform, instead resembling a complex lattice of iron crystals aligned in surprising patterns. Some studies even indicate the inner core might have distinct layers like an onion with different crystalline arrangements at varying depths. The heat here comes from three cosmic sources: residual energy from Earth's violent formation 4.5 billion years ago, the gradual crystallization of the outer core releasing latent heat, and radioactive decay of elements like potassium-40 and thorium-232. Yet despite this thermal onslaught, the pressure is so intense that iron atoms literally cannot move freely enough to melt. Instead, they vibrate in place within a tightly packed hexagonal structure, creating a super-dense material unlike any iron alloy we could produce on the surface. What makes this situation even more fascinating is how it influences our entire planet. The solid inner core's rotation within the liquid outer core generates Earth's magnetic field through a dynamo effect, an invisible force field protecting life from solar radiation. As the core slowly grows by about 1 millimeter per year through crystallization, it releases lighter elements that rise through the outer core, driving convection currents that maintain this vital planetary shield. Without these extreme pressures maintaining a solid inner core, Earth might have lost its magnetic protection eons ago, turning our world into a barren, irradiated wasteland. Recent discoveries have added even more intrigue to this subterranean mystery. Seismic data suggests the inner core might be rotating slightly faster than the rest of the planet, a phenomenon called superrotation completing an extra turn approximately every 400 years. Other studies hint at asymmetric growth patterns, with the core potentially crystallizing faster beneath Indonesia than under Brazil. These subtle dynamics demonstrate that even after billions of years, Earth's deepest realm remains a place of active geological drama, where pressures beyond human comprehension continue to shape the destiny of our planet's surface environment in ways we're only beginning to understand. At the heart of our solar system rages a continuous thermonuclear explosion, the Sun's core, where pressures reach 265 billion times Earth's atmospheric pressure. This unimaginable force creates conditions so extreme that hydrogen atoms, which normally repel each other due to their positive charges, get crushed together with such violence that they overcome electrostatic repulsion and fuse into helium. Each second, 600 million tons of hydrogen undergo this transformation, with about 4 million tons converted directly into energy according to Einstein's famous equation. That's the equivalent of detonating 96 billion 1 megaton nuclear bombs every single second of every day. The process begins when the core's crushing gravity, generated by the Sun's 330,000 times Earth's mass, compresses plasma to densities 15 times greater than solid lead. At these pressures, hydrogen nuclei move so frantically from the heat that when they collide, quantum tunneling allows their protons to momentarily bypass electromagnetic repulsion. Once close enough, the strong nuclear force takes over, welding them together through a multi-step process called the proton-proton chain. First, two protons fuse to form deuterium, a heavy hydrogen isotope, releasing a neutrino and positron. Then that deuterium atom grabs another proton to create helium-3, and finally, two helium-3 nuclei combine to form normal helium-4, spitting out two spare protons to continue the cycle. The energy released from these microscopic collisions manifests as gamma-ray photons, but here's where things get truly bizarre. These photons don't zip straight out to space like you might expect. Instead, they embark on an epic 100,000-year journey through the Sun's dense interior, playing a subatomic game of pinball. Each gamma ray travels barely a millimeter before getting absorbed by surrounding plasma and re-emitted in random directions. This constant absorption and re-emission gradually shifts the photon's energy down through X-rays to ultraviolet and eventually visible light. By the time this energy finally reaches the photosphere, the Sun's visible surface, what began as deadly gamma radiation, has transformed into the warm sunlight that sustains life on Earth. This slow-motion escape happens because the Sun's interior resembles an endlessly crowded subway station during rush hour, with particles packed so tightly that light can't move freely. Scientists call this region the radiative zone, where energy transfers primarily through radiation rather than convection. Only in the outer 30% does the plasma become less dense, allowing hot gas bubbles to rise like boiling water. The convective zone that completes sunlight's long journey. What makes this process so remarkable isn't just its scale, it's the delicate balance that maintains it. The Sun exists in perfect hydrostatic equilibrium, gravity's inward pull precisely counterbalanced by the outward pressure from nuclear fusion. This equilibrium self-regulates like a cosmic thermostat. If fusion rates increase, the core expands slightly to cool down, reducing reactions. If fusion slows, the core contracts, raising pressure and temperature to reignite the process. This feedback loop has kept the Sun shining steadily for 4.6 billion years, with enough hydrogen fuel to continue for 5 billion more. Yet this stability belies the core's ferocity. Temperatures here reach 15 million degrees Celsius, hot enough to vaporize diamonds instantly, while the pressure would crush any human-made material into a quark-gluon soup. It's a place where atoms exist stripped of their electrons as plasma, where the very laws of quantum mechanics become tangible forces, and where the energy from each fusion event, though minuscule, individually combines to power an entire star. Every photon of sunlight warming your skin represents the final step in an epic voyage that began when woolly mammoths still walked the Earth, a testament to the incredible forces churning ceaselessly at the heart of our solar system. Imagine being thrown out of your own galaxy at speeds so extreme you could cross the distance from Earth to the Moon in just 6 minutes. This isn't science fiction, it's the reality for hypervelocity stars, cosmic projectiles racing through intergalactic space at over 1 million kilometers per hour. These stellar fugitives didn't achieve such mind-bending speeds through natural evolution. They're the victims or beneficiaries of one of the universe's most violent gravitational encounters, a close brush with a supermassive black hole. Take star SDSS J090075+2435 for example. Hubble Space Telescope observations revealed this blue-hot runaway hurtling through the Milky Way's outskirts at nearly 2.7 million kilometers per hour, so fast it's destined to escape our galaxy entirely. Astronomers traced its trajectory backward to the galactic center, where our own supermassive black hole, Sagittarius, a star, likely slingshotted it outward in a cosmic game of gravitational pinball. The physics behind this ejection is as elegant as it is brutal. When a binary star system wanders too close to a black hole, one star gets captured while the other gets flung away at incredible speeds like a stone from a sling. What makes these stars so fascinating isn't just their speed, it's what they reveal about the environments that spawn them. Their trajectories serve as cosmic breadcrumbs, pointing directly back to the black holes that launched them. In 2013, astronomers discovered one hypervelocity star moving so fast it couldn't have originated from the Milky Way, meaning it was likely ejected by the supermassive black hole in Andromeda, our nearest galactic neighbor. These intergalactic refugees become unwitting messengers, carrying information about distant black holes we couldn't study otherwise. The survival of these stars during their violent ejection is equally remarkable. Most hypervelocity stars detected are massive blue stars, stellar heavyweight champions with 10 to 15 times the Sun's mass. Smaller, cooler stars would likely be torn apart during the acceleration process, but these giants withstand the gravitational abuse, though not without scars. Spectroscopic analysis shows many have distorted shapes from their ordeal, stretched like taffy by tidal forces during their close encounter. Some even exhibit unusual chemical compositions, their outer layers stripped away to reveal fusion products normally hidden deep in their cores. Beyond their origin stories, hypervelocity stars offer scientists a unique opportunity to map the Milky Way's gravitational field. Their paths, unimpeded by gas clouds or star clusters, respond only to the galaxy's overall mass distribution. Like probes sent through unseen terrain, Their trajectories reveal the invisible scaffolding of dark matter holding our galaxy together. And because they travel so far so quickly, they become natural experiments in stellar evolution, showing how stars behave when isolated from the dense environments where they typically form. Perhaps most poetically, these stellar outcasts embody a universal truth that destruction and creation often go hand in hand. While their fellow star met a grim fate spiraling into the black hole, these survivors gained something extraordinary: freedom from the crowded galactic disk, a one-way ticket to the quiet vastness of intergalactic space. Billions of years from now, long after the Milky Way and Andromeda collide and merge, these rogue stars will still be drifting through the cosmic void, solitary witnesses to the dynamic forces that shape them. While black holes and neutron stars showcase gravity's crushing might, the universe harbors an opposite extreme: regions where space itself seems to push outward with a strange anti-gravity force. This phenomenon, called dark energy, creates what physicists describe as negative pressure, a cosmic tension stretching the fabric of spacetime apart. Unlike anything we encounter in daily life, this pressure doesn't come from particles pushing against each other, but from space itself expanding between them. The emptier space becomes, the stronger this repulsive effect grows, accelerating the universe's expansion in what may be its ultimate fate. The Boötes void offers a staggering example of this principle in action. Spanning 330 million light-years, this cosmic desert contains just 60 galaxies where thousands should exist, making it one of the emptiest places known. Here, dark energy's influence becomes palpable. As the void grows emptier over billions of years, the negative pressure within it subtly strengthens, creating a self-reinforcing cycle where expansion begets more expansion. Galaxies at the void's edges appear to recede faster than Hubble's law predicts, as if space itself were slipping away like sand through open fingers. What makes dark energy's negative pressure so baffling is how it inverts everything we know about forces. Normal pressure, like air in a tire, resists compression. But this cosmic tension actively resists being reduced. The more you try to squeeze it, the harder it pushes back. Quantum field theory suggests this might arise from temporary particle-antiparticle pairs flickering in and out of existence in empty space, though calculations predict a value 120 orders of magnitude larger than observed, the worst mismatch in physics history. This cosmological constant problem remains unsolved, with some theorists proposing entirely new physics involving extra dimensions or dynamic fields. The implications are profound. If dark energy's negative pressure persists, it could lead to a Big Rip scenario where even atoms get torn apart as space's expansion overcomes all binding forces. Alternatively, it might gradually isolate galaxy clusters in separate causal bubbles, freezing the universe into eternal darkness. Current measurements suggest this expansion accelerates by about 74 kilometers per second per megaparsec, meaning each cubic meter of space contains roughly 100 attojoules of dark energy, a whisper-thin tension that nonetheless dominates the cosmos. Yet for all its strangeness, this negative pressure might hold clues to the universe's origin. Some models suggest similar repulsive gravity-powered inflation, the explosive expansion right after the Big Bang. Others speculate it could relate to vacuum energy transitions between different quantum states. As astronomers map more supervoids like Boötes, they're essentially taking the universe's blood pressure, measuring how its empty regions pulse and grow over cosmic time. The results may reveal whether dark energy is truly constant, or if we're witnessing the early stages of something even more exotic rewriting the rules of cosmic expansion. Some of the universe's most precious treasures aren't found in the ground, they are forged in the spectacular collisions of dead stars. When two neutron stars spiral together in a cosmic dance of doom, they don't just create gravitational waves, they become gold factories, synthesizing enough precious metals in seconds to outweigh entire planets. This process, called rapid neutron capture or the R process, is nature's ultimate alchemy, transforming ultra-dense stellar remnants into the very elements that adorn our fingers and fill our electronics. The historic detection of GW170817 in 2017 gave us a front-row seat to this extraordinary phenomenon. As LIGO gravitational wave detectors picked up the telltale spacetime ripples from a collision 130 million light-years away, telescopes worldwide swiveled to catch the aftermath, a kilonova explosion glowing with the heat of newly created elements. The data revealed something astonishing. During the brief cosmic crash, conditions became so extreme that free neutrons flooded the environment at densities surpassing Earth's atmosphere by orders of magnitude. These neutrons slammed into atomic nuclei at breakneck speeds, building heavier and heavier elements in a chain reaction that synthesized an estimated 10 Earth masses of pure gold, along with vast quantities of platinum, uranium, and other rare metals. What makes this process so remarkable is how it solves a long-standing cosmic mystery. For decades, scientists struggled to explain where half the universe's heavy elements originated. Regular supernova can't provide enough neutrons for the R process, and the cores of massive stars lack the necessary conditions. But neutron-star mergers, with their unparalleled densities and temperatures, create the perfect neutron-rich pressure cooker. Simulations show the collision's shockwaves ejecting neutron-laden material at up to 30% light speed, forming expanding clouds where atomic nuclei grow like snowflakes in a blizzard, grabbing neutrons faster than they can radioactively decay. The aftermath of GW170817 provided smoking gun evidence. Spectroscopic analysis of the kilonova's light revealed characteristic absorption lines from strontium and other R-process elements, while the explosion's distinctive redshift over days matched predictions for radioactive decay of freshly minted heavy nuclei. Even more telling, the event produced about 100 times more lanthanides than our entire solar system contains, proving neutron-star collisions could indeed be the universe's primary source of these precious materials. This revelation connects us to the cosmos in profound ways. Every gold ring or platinum necklace contains atoms likely born in such catastrophic mergers billions of years before our sun formed. Some researchers estimate that a single neutron-star collision could seed thousands of future solar systems with enough heavy elements to form rocky planets and perhaps life itself. As we continue hunting for more kilonovae with next-generation observatories, each discovery peels back another layer of our celestial origins, revealing how the universe's most violent events create the building blocks of everything we hold valuable. To witness the universe in its infancy, we must venture into a realm where matter as we know it ceases to exist, a seething ocean of unbound quarks and gluons known as quark-gluon plasma. This primordial soup, hotter than 10 trillion degrees Celsius, represents the state of all matter mere microseconds after the Big Bang, when the cosmos was too frenzied and dense for even protons and neutrons to form. At these unimaginable temperatures and pressures, the strong nuclear force which normally binds quarks into particles becomes overpowered, leaving these fundamental building blocks to roam freely like ingredients in a cosmic broth. Scientists at Brookhaven's relativistic heavy ion collider, RHIC, have recreated these conditions by smashing gold nuclei together at 99.999% of light speed. These ultra-relativistic collisions generate fleeting fireballs smaller than an atom yet hotter than a supernova, where quarks and gluons break free from their usual confines for just a yoctosecond, a septillionth of a second. Detectors surrounding the collision point capture the aftermath, revealing a surprising truth. This plasma behaves less like a gas and more like a frictionless liquid, flowing with near-perfect fluidity despite its mind-boggling energy density. The phenomenon mirrors what theorists predict occurred when the universe was just 1/1,000,000th of a second old, before cooling enough for quarks to freeze out into the protons and neutrons we know today. What makes these experiments revolutionary isn't just their recreation of cosmic history, it's how they challenge our understanding of matter's fundamental nature. The quark-gluon plasma's unexpected liquidity suggests quarks interact far more strongly when freed than predicted, while its opacity to certain particles hints at deeper quantum complexities. Some collisions even produce exotic quark molecules, temporary configurations unseen in nature for over 13 billion years. Perhaps most astonishing is how this research connects to the universe's largest structures. The same physics governing quark-gluon plasma may explain how asymmetries in the early universe seeded galaxy formation. By studying these microscopic fireballs, we're effectively running the universe's first moments in reverse, peering into an era when everything that exists was compressed into a form so extreme it defies all everyday experience. And hidden within that data might lie answers to lingering mysteries, like why the cosmos contains so much more matter than antimatter, or whether even quarks themselves are made of smaller constituents. These experiments don't just illuminate the past, they reveal the extraordinary potential locked within ordinary matter. Every proton in your body spent its first moments in this exotic state, a relic of when the entire universe existed as a single, unimaginably hot droplet of pure energy. The quark-gluon plasma isn't just a scientific curiosity, it's the original blueprint for everything we are. Not all planets enjoy the warmth of a parent star. Some wander the cosmos alone, cast out from their birth systems in gravitational upheavals we can scarcely imagine. These rogue planets drift through the interstellar void, untethered from any sun, enduring temperatures barely above absolute zero and relentless bombardment by cosmic rays. One such wanderer, CFBT SIR 2149-0403, was discovered adrift just 100 light-years away, a Jupiter-sized orphan with a faint infrared glow from its residual heat, slowly bleeding into the frigid darkness around it. The journey from stable planet to cosmic nomad begins with gravitational chaos. When young solar systems form, close encounters between massive planets can fling smaller worlds outward like stones from a slingshot. In other cases, passing stars or galactic tides may perturb orbits just enough to send a planet careening into interstellar space. Simulations suggest our own Milky Way could harbor billions, perhaps trillions of these dark wanderers, outnumbering stars by as much as 20 to 1. Without a host star's light to reveal them, they're nearly invisible, detectable only through rare microlensing events where their gravity briefly bends light from distant stars. The conditions these frozen exiles endure defy earthly imagination. Surface temperatures plunge below -250 degrees Celsius, so cold that even gaseous atmospheres freeze solid, forming exotic ices of nitrogen and carbon monoxide. Without stellar winds to shield them, their surfaces bake in constant particle radiation, stripping away any remaining atmosphere over eons. Some may retain subterranean oceans kept liquid by radioactive decay or tidal heating from surviving moons, potential refuges for life in perpetual night. Yet rogue planets aren't necessarily eternal ice tombs. A few might harbor volcanic activity fueled by internal heat, creating cryovolcanoes spewing ammonia or methane instead of lava. Others could generate weak magnetic fields through conductive metallic hydrogen layers, offering fleeting protection from cosmic rays. Artist renditions often depict these worlds as frozen wastelands, but their reality could be far stranger: sheets of neon ice glowing under cosmic radiation, or diamond-encrusted cores formed under immense pressures during ejection. What makes their existence so profound is how it rewrites the definition of a planet. No longer bound to orbiting stars, these nomads challenge our solar system's centric worldview, proving planets can form and exist independently. Some theories even suggest rogue planets could outlast their stellar counterparts, surviving unscathed when all stars have burned out, becoming the longest-lasting objects in the universe. As our detection methods improve, each new discovery peels back another layer of their mystery, revealing a galaxy far richer in wandering worlds than we ever dared imagine. Somewhere in the depths of intergalactic space, an unseen force is tugging at our entire cosmic neighborhood with enough strength to pull galaxies at 14 million miles per hour. This cosmic tractor beam, known as the Great Attractor, has puzzled astronomers since its discovery in the 1970s. A gravitational anomaly so powerful it bends the paths of hundreds of galaxies, including our own Milky Way, toward a mysterious point in space we can't even see clearly. The challenge in studying this phenomenon comes from its unfortunate position directly behind the dense star fields and dust clouds of our galaxy's disk, in the direction of the constellation Centaurus. Imagine trying to spot a lighthouse through a blizzard. That's what astronomers face when observing this region. The Milky Way's galactic plane blocks visible light, forcing researchers to rely on X-ray and radio telescopes to peer through the cosmic smokescreen. What they've found is staggering: a concentration of mass equivalent to tens of thousands of Milky Ways, pulling galaxies across 600 million light-years into what scientists call the Laniakea supercluster, our home supercluster of galaxies. The leading theory suggests the Great Attractor isn't a single massive object, but rather the dense core of this supercluster, where galaxy density spikes dramatically. At its heart lies the Norma cluster, a tight knot of galaxies and hot gas emitting powerful X-rays, but even this can't fully account for the observed gravitational pull. Some researchers propose dark matter, the invisible scaffolding of the cosmos, forms an especially dense web here, amplifying the attraction beyond what visible matter could produce. Others speculate there might be something even larger beyond it, like the Shapley supercluster, exerting its influence from over 650 million light-years away. What makes this cosmic tug-of-war particularly fascinating is how it demonstrates the hierarchy of the universe's structure. Just as Earth orbits the Sun and the Sun moves around the Milky Way, our entire galaxy, along with Andromeda and other local group members, is being drawn toward this distant gravitational focal point. Advanced simulations show this motion isn't straightforward. Galaxies flow along great cosmic filaments like leaves caught in a river's current, with the Great Attractor acting as a whirlpool in this intergalactic stream. The mystery deepens when we consider the universe's expansion. While dark energy pushes most galaxies apart at accelerating rates, the Great Attractor's local gravity overpowers this expansion, creating a rare region where the cosmic tide still flows inward. Future observations with next-generation telescopes promise to unveil more of this hidden gravitational heart, potentially rewriting our understanding of how matter organizes itself across the largest scales of the cosmos. Until then, it remains one of astronomy's greatest puzzles, an unseen hand guiding the motion of galaxies, including our own, through the vast intergalactic void. Gamma-ray bursts stand as the universe's most violent electromagnetic explosions, cosmic death beams capable of sterilizing entire planetary systems in seconds. These fleeting but cataclysmic events unleash more energy in milliseconds than our Sun will emit across its 10 billion-year lifetime, channeled into narrow jets moving at 99.999% of light speed. When such a beam crosses paths with a hapless planet, the effects would make nuclear war look like a sparkler, an immediate barrage of high-energy radiation stripping atmospheres, triggering mass extinctions, and baking surfaces with X-ray fluxes 1,000,000 times stronger than solar flares. The Swift satellite has given us front-row seats to this celestial fireworks show since 2004, detecting hundreds of bursts across the observable universe. One particularly monstrous event, JABI 080319b, erupted 2.6 billion light-years away, yet briefly outshone every star in our galaxy combined. Its afterglow remained visible to amateur telescopes for nearly a week, a testament to the unfathomable energies involved. Analysis revealed this burst likely originated from a quasar, a rapidly spinning massive star collapsing directly into a black hole. Its death throws powering relativistic jets that punch through the stellar corpse like a cosmic blowtorch through butter. What makes these events so terrifyingly efficient is their focused brutality. Unlike supernova that explode in all directions, gamma-ray bursts concentrate their fury into pencil-thin beams. This collimation means most bursts go undetected. We only see them when Earth happens to lie within the jet's narrow path. Statistically, one likely hits our galaxy every few million years. Geological evidence suggests a gamma-ray burst may have triggered the late Ordovician mass extinction 450 million years ago, stripping Earth's ozone layer and bombarding the surface with enough UV radiation to decimate marine life. Yet for all their destructive potential, these bursts also serve as cosmic lighthouses. Their afterglows allow astronomers to probe the composition of intergalactic space across billions of light years. Some long-duration bursts even correlate with supernova, acting as birth announcements for newborn black holes. The most distant known burst, GRB 090429b, detonated when the universe was just 520 million years old, its light carrying clues about the first generations of stars. Perhaps most remarkably, we now know neutron star mergers can produce short gamma-ray bursts, a revelation confirmed by the landmark GW 170817 detection. When those two stellar corpses collided, they didn't just create gravitational waves and forge gold, they launched a relativistic jet visible as GRB 170817a. This multi-messenger event proved catastrophic stellar deaths can wear many faces: gravitational waves, kilonovae, and these deadly beams all originating from the same unfathomably violent cosmic crucible. As observatories grow more sophisticated, each new burst peels back another layer of their mystery. Some exhibit bizarre substructures, millisecond spikes within the main emission suggesting turbulent processes in the jet engine. Others show prolonged X-ray plateaus hinting at continuous energy injection from a newborn magnetar. What remains undisputed is their status as nature's ultimate particle accelerators, natural laboratories where matter gets stretched, shredded, and accelerated to energies dwarfing anything human-made. For all their destructive potential, gamma-ray bursts illuminate the extreme physics governing our universe's most energetic phenomena. Astronomers are facing a cosmic conundrum so baffling it might rewrite our fundamental understanding of the universe, the Hubble tension. At its heart lies a stubborn discrepancy in how fast space is stretching apart, with different measurement techniques yielding conflicting results that grow more pronounced with each passing year. On one side, we have meticulous observations of the cosmic microwave background by the Planck satellite, the afterglow of the Big Bang, painting a picture where space expands at 67.4 kilometers per second per megaparsec. On the other, measurements of distant supernova and pulsating stars suggest a significantly faster expansion rate of 73 kilometers per second per megaparsec. That 5.6-kilometer difference might sound trivial, but in cosmology terms, it's like discovering your car's speedometer and GPS are violently disagreeing while barreling down the highway. The Planck measurements rely on the universe's baby photos, snapshots of primordial light from when the cosmos was just 380,000 years old. By analyzing subtle temperature variations in this cosmic background radiation, scientists can extrapolate how space should be expanding today, assuming standard physics holds true. Meanwhile, the supernova method acts as a cosmic ruler, using the predictable brightness of exploding white dwarfs called Type Ia supernova to gauge distances across billions of light years. These stellar explosions serve as standard candles, their uniform peak luminosity allowing astronomers to calculate how much the universe has stretched since their light began traveling toward us. The fact these two gold standard techniques disagree suggests something fundamental might be missing from our models. What makes this tension so electrifying is what it implies about the universe's contents. The Planck data fits beautifully with our current understanding of dark energy comprising 69% of the cosmos, dark matter 26%, and normal matter a mere 5%, the so-called lambda-CDM model. But the supernova results demand adjustments that could mean dark energy isn't constant as we've assumed, but evolving over time. Some theorists propose it might be growing stronger, while others suggest we're seeing hints of extra dark matter particles or even modifications to Einstein's gravity at cosmic scales. The most radical ideas invoke parallel universes exerting gravitational pull on ours, or quantum entanglement between our universe and others in the multiverse. This isn't just academic quibbling. The Hubble tension threatens to upend our cosmic timeline. If the faster local measurements hold, the universe might be younger than we thought by over 1 billion years. Alternatively, unknown early universe phenomena could have left imprints that skew our interpretation of the cosmic microwave background. New observational tools are joining the fray to resolve this mystery. The James Webb Space Telescope's pristine infrared vision is recalibrating distance measurements to Cepheid variable stars, while next-generation cosmic microwave experiments like the Simons Observatory will remap the ancient sky with 10 times Planck's precision. Perhaps most exciting is what this conflict reveals about science in action. The Hubble tension represents that rare moment when nature refuses to conform to our best theories, forcing us to question assumptions we've held for decades. Whether it leads to tweaking cosmological parameters or discovering entirely new physics, one thing is certain: the universe still has surprises up its sleeve, and the tools to uncover them are finally catching up to our curiosity. Dark matter remains the universe's most enigmatic architect, an invisible hand sculpting cosmic structures through gravity alone. While ordinary matter makes up stars, planets, and everything we see, this mysterious substance outmasses it 5 to 1, weaving an unseen scaffold that determines the fate of galaxies. The Bullet Cluster offers perhaps the most striking demonstration of dark matter's reality, a galactic collision where observable matter and gravitational effects visibly divorced. When these two galaxy clusters plowed through each other at millions of miles per hour, their visible gas clouds, seen in X-rays, slammed together like interstellar fog, glowing hot from the impact. But something extraordinary happened to the cluster's mass, mapped through gravitational lensing. The bulk of their gravity stayed with the galaxies rather than the gas, revealing dark matter streaming through the wreckage like a ghostly shadow untouched by the collision. This cosmic car crash proved dark matter isn't just theoretical. Unlike normal particles, these unseen components barely interact with each other or light. They pass through the collision like silent spectators, while regular matter got caught in a traffic jam of electromagnetic forces. The aftermath shows two distinct components: pinkish clouds of hot gas marking where baryonic matter piled up, and blue haze representing the lensing effect of dark matter's gravity still aligned with the galaxies. This separation becomes nature's ultimate forensic evidence, demonstrating that what we call empty space holds nearly 90% of a galaxy cluster's mass. The implications ripple across cosmology. Dark matter's gravitational pressure acts like an invisible glue, preventing rapidly rotating galaxies from flying apart. Computer simulations show without it, spiral arms would unravel and galactic disks would disintegrate within a few rotations. Its presence explains why galaxies in clusters orbit faster than their visible mass should allow, and how the universe formed its intricate web-like structure so quickly after the Big Bang. Observations of the cosmic microwave background reveal dark matter's gravitational fingerprints were already sculpting tiny density fluctuations when the universe was just 100,000 years old, seeds that would later grow into galaxies and clusters. Yet for all its dominance, dark matter remains stubbornly elusive. Experiments deep underground search for rare interactions with exotic particles. particle accelerators attempt to create it momentarily. Even gravitational wave detectors might eventually sense its subtle tremors. What makes this hunt so compelling is how it challenges our understanding of reality. We're surrounded by an invisible ocean of mass that shapes everything we see, yet passes through our bodies undetected every second. The bullet cluster didn't just prove dark matter exists, it revealed a universe far stranger than we imagined, where most of creation hides in plain sight. Imagine looking at the afterglow of the Big Bang and seeing ghostly fingerprints pressed into its surface distortions that reveal the hidden architecture of the universe. That's precisely what the Sunyaev-Zeldovich effect allows astronomers to do. As the ancient light from the cosmic microwave background travels across the cosmos, it passes through vast clouds of superheated gas trapped within galaxy clusters. These scorching plasma clouds, heated to tens of millions of degrees, act like cosmic lenses, but instead of bending light, they give it an energy boost through sheer pressure. Here's how this remarkable phenomenon works. When low-energy photons from the cosmic microwave background encounter the high-energy electrons in these gas clouds, they gain a small kick like a ping-pong ball being hit by a speeding train. This interaction, known as inverse Compton scattering, slightly shifts the photon's wavelengths, creating detectable shadows and bright spots in the microwave sky. The astonishing part, these distortions trace not just the hot gas itself, but the gravitational scaffolding of dark matter that holds the entire cluster together. The bullet cluster offers a textbook example. When astronomers mapped its Sunyaev-Zeldovich effect, they found the hot gas visible through X-rays lagging behind the cluster's gravitational center, which was revealed by the distorted microwave background patterns. This separation provided smoking gun evidence that most of a galaxy cluster's mass exists in an invisible form, guiding the hot gas like an unseen hand. Modern telescopes like the Atacama Cosmology Telescope and the South Pole Telescope now use this effect to map thousands of clusters across billions of light-years, essentially turning galaxy clusters into gigantic dark matter detectors. What makes this cosmic shadow play so revolutionary is its ability to reveal structure where optical telescopes see nothing. Unlike traditional methods that rely on visible light, the Sunyaev-Zeldovich effect works equally well whether a cluster is nearby or at the edge of the observable universe. It even detects so-called empty regions where galaxies haven't fully formed yet, but where dark matter's gravitational pull is already sculpting future cosmic metropolises. Some of the most distant clusters ever discovered were found not by their starlight, but by their subtle fingerprints on the ancient afterglow of creation. This effect doesn't just map dark matter, it's rewriting our understanding of cosmic evolution. By comparing Sunyaev-Zeldovich maps with computer simulations, scientists can test theories about how dark matter shapes the universe's large-scale structure. Recent measurements suggest some clusters contain more hot gas than predicted, hinting at complex interactions between dark matter and ordinary matter we're only beginning to understand. Others reveal mysterious voids where the microwave background appears cooler than expected, possibly signaling energy exchanges on scales we've never before been able to probe. At its core, the Sunyaev-Zeldovich effect represents a brilliant workaround to one of astronomy's greatest challenges: how to study what we can't see directly. By observing how the universe's oldest light gets tweaked and twisted on its 14 billion-year journey to our telescopes, we're essentially reading cosmic tea leaves written in the language of shadow and pressure. Each distortion tells a story of dark matter's invisible grip, of galaxies yet to form, and of a universe far stranger and more interconnected than we ever imagined. On the scorching exoplanet WASP-76b, the laws of weather take a sinister turn where iron doesn't just melt, but falls from the sky in glowing metallic downpours. This ultra-hot Jupiter, orbiting perilously close to its host star, presents one of the most dramatic examples of tidal locking in the cosmos, one face forever blistering under relentless stellar fury, while the other languishes in perpetual twilight. The temperature contrast across this world is so extreme that it rips apart the very concept of atmospheric equilibrium. 2400 degrees Celsius on the day side, hot enough to vaporize iron, titanium, and even silicates into shimmering metallic clouds, while the night side plunges to a relatively cool 1000 degrees, allowing these vapors to condense into droplets of molten metal that rain downward through pitch-black skies. Spectroscopic observations from the espresso instrument revealed this nightmare weather in startling detail. As the planet's atmosphere circulates from day to night, supersonic winds exceeding 11,000 miles per hour carry vaporized metals into the twilight zone, where they abruptly cool and liquefy. The result is a perpetual storm of liquid iron precipitation, illuminated only by the dull red glow of its own superheated droplets. Unlike Earth's water cycle, where evaporation and condensation occur within a narrow temperature band, WASP-76b operates on a metallurgical scale, its entire atmosphere acting like a colossal distillation furnace, separating and recombining elements in a continuous, hellish loop. What makes this world particularly fascinating is how it challenges our understanding of atmospheric chemistry. Most exoplanet models assumed metals would remain uniformly distributed, but here we see them segregating like oil and water on a planetary scale. The dayside's extreme heat breaks molecules into their component atoms, while the nightside's cooler temperatures allow exotic compounds like iron hydride to form, molecules never stable on Earth. Recent Hubble data even suggests the iron rain might be snowing sideways due to howling crosswinds, creating horizontal sheets of molten metal suspended in the upper atmosphere. Yet perhaps the most haunting implication lies in the planet's origin story. WASP-76b likely formed much farther out in its system, migrating inward over eons until its rotation synchronized with its orbit, a process that superheated its atmosphere while leaving the night side just cold enough for this macabre metal cycle to begin. It's a stark reminder that the universe harbors environments far beyond earthly extremes, worlds where the very elements we consider solid and stable become volatile participants in weather systems beyond imagination. And as we discover more ultra-hot Jupiters, each one peels back another layer of how matter behaves when pushed to its absolute limits. Far beyond the orbits of Neptune and Pluto, where sunlight dwindles to a faint whisper, lies a frozen vault holding our solar system's most pristine artifacts, the Oort cloud. This spherical shell of icy debris stretches nearly a light year into the void, a graveyard of primordial material untouched by the heat and turbulence that reshaped the inner planets. Here, in the profound cold of interstellar space, pressures hover just above absolute zero, suspending cometary nuclei in a state of cosmic deep freeze for 4.6 billion years. These icy time capsules contain chemical fingerprints from the solar nebula's earliest moments, preserved with such exquisite clarity that scientists consider them refrigerators of the solar system's infancy. Among these drifting relics, Comet C2014Q2 Lovejoy delivered a bombshell discovery in 2015. As it ventured improbably close to the Sun, astronomers detected ethyl alcohol and simple sugars in its vapor trail, organic compounds essential for life, surviving unchanged since the solar system's birth. This suggests the Oort cloud may have been the universe's original chemical pantry, storing probiotic ingredients that later rained down on young worlds like Earth during the heavy bombardment period. Other Oort cloud visitors, like the famed comet Hale-Bopp, revealed traces of argon and nitrogen isotopes matching theoretical predictions about our solar system's formation, temperature, direct evidence that these icy wanderers formed in the same protoplanetary disk as Earth, but avoided the melting and differentiation that erased such clues from terrestrial planets. The extreme environment of the Oort cloud plays a crucial role in this preservation. with temperatures hovering around 5 degrees above absolute zero and pressures millions of times weaker than Earth's atmosphere. Chemical reactions progress at glacial speeds, literally. A water molecule sublimating from one of these primordial icebergs might take centuries to travel just a few meters. This near-perfect stasis means delicate crystalline structures in the ice, delicate organic molecules, and even pockets of ancient interstellar dust survive unaltered, shielded from the erosive effects of solar wind and cosmic rays by their tremendous distance. Yet this frozen archive isn't static. Gravitational nudges from passing stars or galactic tides occasionally send a cometary nucleus spiraling inward, transforming it from a frozen time capsule into a blazing apparition in our night sky. When Comet Ison approached in 2013, its composition suggested it was making its first journey sunward after 4.5 billion years in deep freeze, making its destruction by solar tides all the more tragic for researchers. These infalling comets act as celestial Rosetta Stones, delivering samples from the solar system's outermost reaches that we could never hope to retrieve with spacecraft. What makes the Oort cloud truly humbling is its scale. Current estimates suggest it contains trillions of objects with a combined mass potentially exceeding 40 times Earth. Some of these icy bodies likely originated closer to the Sun before being hurled outward by gravitational encounters with Jupiter and Saturn during the solar system's chaotic early days. Others might be interstellar interlopers captured by the Sun's gravity, like the mysterious Oumuamua in 2017. This means the Oort cloud could hold not just secrets of our solar system's formation, but frozen fragments of alien star systems, making it the ultimate cosmic attic, storing forgotten treasures from across both space and time. Hanging above and below the Milky Way's center like cosmic hourglasses, the Fermi bubbles stand as one of our galaxy's most colossal structures. Twin towers of high-energy gamma rays stretching 25,000 light-years into intergalactic space. Discovered in 2010 by NASA, a Fermi Gamma-Ray Space Telescope, these gargantuan formations glow with the aftermath of an unfathomable energy release from our galaxy's supermassive black hole, Sagittarius, a star between 1 and 3 million years ago. Picture two spheres of searing plasma, each large enough to contain 15,000 Milky Ways placed end to end, projecting perpendicular to our galactic disk like the bellows of some celestial forge. What makes these structures so extraordinary is their composition, not just hot gas, but cosmic ray particles accelerated to nearly light speed, colliding with interstellar material to produce the gamma rays that make the bubbles visible. The edges act like shock fronts with temperatures reaching millions of degrees, while the interiors contain magnetic field lines twisted like spaghetti by the original outburst. When astronomers first mapped them, they expected symmetrical spheres, but the bubbles revealed startling asymmetry. The northern bubble extends slightly farther than its southern counterpart, suggesting our black hole's eruption wasn't perfectly balanced. Some theories propose this lopsidedness stems from the black hole's spin axis tilting relative to the galactic plane, or perhaps uneven gas distribution in the surrounding regions when the eruption occurred. Diving deeper into their origins, scientists reconstruct a cataclysmic event called a Seyfert flare, a black hole-feeding frenzy where Sagittarius, a star, likely devoured an enormous gas cloud or perhaps even a star cluster. As matter spiraled inward at relativistic speeds, some got channeled along the black hole's rotation axis and blasted outward in opposing jets, punching through the galactic disk and inflating these colossal cavities. The energy required staggers the imagination, equivalent to hundreds of supernovae detonating simultaneously, yet remarkably, this outburst left Earth unharmed due to our solar system's position about 27,000 light-years from the center. Modern observations reveal even richer structures within the bubbles. The Rossat X-ray telescope discovered CAP regions with particularly intense emission, possibly marking where the outflow collided with pre-existing gas clouds in the galactic halo. Meanwhile, ultraviolet spectra from the Hubble Space Telescope detected high-velocity clouds streaming along the bubble's surfaces like interstellar rivers, their composition hinting at material torn from the galactic disk during the eruption. These features act as forensic evidence, allowing astronomers to estimate the outburst lasted between 10,000 and 100,000 years, a cosmic blink lasting shorter than human civilization's existence. The Fermi bubbles aren't just relics of past violence, they're actively shaping our galaxy's future. By venting hot gas into the galactic halo, they regulate star formation across the Milky Way, preventing excessive cooling that could trigger runaway stellar birth in the central regions. Their ongoing expansion stirs the surrounding interstellar medium, redistributing heavy elements forged in supernova and potentially influencing the orbits of globular clusters orbiting the galactic center. Some researchers even speculate these structures might explain certain high-energy cosmic rays detected at Earth, particles accelerated by shock waves still rippling through the bubble's boundaries millions of years after the initial cataclysm. Perhaps most remarkably, similar structures have now been spotted in other galaxies, suggesting black hole outbursts might be a universal mechanism for galactic regulation. The bubbles serve as a stark reminder that even seemingly quiet galaxies like ours have violent hearts, capable of eruptions that reshape their surroundings on scales dwarfing anything in the local universe. And buried within their gamma-ray glow lies an unsettling implication. Given the right cosmic trigger, our galactic center could awaken again, unleashing another outburst that would reverberate through the Milky Way for eons to come. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a 72-second burst of radiation so perfectly matched to extraterrestrial expectations that the astronomer who discovered it circled the signal on the printout and simply wrote, "Wow." Next to it, this fleeting cosmic transmission, 30 times stronger than background noise and confined to a narrow frequency band where hydrogen naturally resonates, remains one of the most tantalizing mysteries in the search for intelligent life. Yet despite decades of searching, the signal never repeated, leaving scientists with a single tantalizing data point, a cosmic whisper from the void that continues to defy explanation. The WOW signal's uniqueness lies in its precise characteristics. Broadcasting at 1420 MHz, the frequency of neutral hydrogen, the most abundant element in the universe, the transmission showed all the hallmarks of an engineered signal. It wasn't random noise, but a focused beam that rose and fell in intensity exactly as expected if originating from deep space and passing through Earth's rotating telescope field of view. Modern analysis suggests if it came from a fixed point beyond our solar system, the source would need to be as powerful as a focused planetary radar or an interstellar beacon, technology theoretically within an advanced civilization's capabilities. The decades since have seen SETI search for extraterrestrial intelligence evolve from single telescope observations to coordinated international efforts. Projects like Breakthrough Listen now use artificial intelligence to scan millions of radio channels simultaneously across multiple telescopes, searching for patterns that might resemble the WOW signal's distinctive fingerprint. The Allen Telescope Array in California, with its 42 dish antennas, can monitor several star systems at once, while newer optical SETI programs look for nanosecond laser pulses that could represent interstellar communication attempts. Ironically, the same advancements confirming the WOW signal's unusual nature have also deepened the mystery. Recent research suggests natural explanations, like hydrogen clouds magnifying distant radio sources through interstellar lensing, or even a pair of comets emitting transient radio bursts as they passed through that region of space in 1977. Yet none fully account for the signal's intensity and frequency purity. The most chilling possibility remains that we intercepted a one-time transmission, perhaps an alien civilization's long-defunct beacon, or a targeted message that swept past Earth like a searchlight beam and vanished forever. Modern SETI has learned crucial lessons from this enigmatic event. Instead of passively waiting for repeats, new initiatives like Project Galileo actively monitor the original WOW. Signals celestial coordinates using sensitive radio arrays. Other programs catalog similar transient anomalies, building databases of potential technosignatures. The Vera C. Rubin Observatory, set to begin operations soon, will image the entire visible sky every few nights, potentially catching optical counterparts to any future radio burst. What makes the WOW signal endure isn't just its mystery, it's how it reshaped our cosmic perspective. For 72 seconds, humanity may have glimpsed evidence that we're not alone in the universe. Whether natural phenomenon or alien hello, its legacy continues to inspire the telescopes scanning the stars tonight, listening for another whisper in the cosmic dark. For less time than it takes to blink, certain points in the cosmos unleash more energy than our sun produces in 3 days, fast radio bursts, the universe's most mysterious and violent radio flashes. These pulses last mere milliseconds yet pack staggering power, their electromagnetic energy equivalent to 500 suns beaming at once. Since their accidental discovery in 2007 by astronomers combing through archived pulsar data, these cosmic firecrackers have defied explanation, appearing unpredictably across the sky before vanishing without trace. One burst in particular rewrote the rulebook FRB 12-1102, detected in 2012 by the Arecibo telescope. Unlike its one-off cousins, this source did something unprecedented. It repeated. Over years of observation, astronomers catalogued hundreds of bursts from this single object, tracing its origin to a surprising home, a tiny, ramshackle dwarf galaxy 3 billion light-years away. This unassuming stellar nursery, barely 1% the Milky Way's mass, became ground zero for solving one of astronomy's greatest puzzles. The repeating pattern ruled out catastrophic one-time events like neutron star collisions, narrowing possibilities to extreme objects capable of surviving multiple eruptions, magnetars with their incomprehensible magnetic fields, or black holes tangled in cosmic webs of plasma. What makes these bursts so fascinating isn't just their energy, it's how they illuminate the intergalactic medium like a flashlight through fog. As the radio waves traverse cosmic distances, they interact with electrons along their path, allowing astronomers to measure the universe's missing matter, ionized gas too diffused to detect otherwise. Some bursts even exhibit bizarre polarization twists, suggesting they pass through regions with magnetic fields billions of times stronger than Earth's, possibly near neutron stars or black hole accretion disks. The detective work continues with next-generation instruments. The Canadian Hydrogen Intensity Mapping Experiment has become a prolific burst hunter, its array of radio dishes pinpointing dozens of new sources. Meanwhile, the Deep Synoptic Array in California combines hundreds of antennas to localize bursts within individual host galaxies, revealing an astonishing diversity. Some emanate from quiet, ancient galaxies, others from regions of furious star formation. One even originated inside our own Milky Way, definitively linked to a hyperactive magnetar, though this local burst was thousands of times weaker than its extragalactic cousins, deepening the mystery. Theories abound colliding neutron stars, cosmic strings snapping like rubber bands, or even, more speculatively, alien propulsion systems harnessing unimaginable energies. Current frontrunners involve starquakes on magnetar surfaces, where shifting crusts release magnetic energy in catastrophic ruptures, or blitzars, overweight neutron stars collapsing into black holes and shedding their magnetic envelopes in explosive farewells. With each new detection, the picture grows more complex. Recent observations of FRB 21-20204 revealed something unprecedented, a burst lasting 3 full seconds, 1,000 times longer than typical, with periodic substructures repeating every 0.2 of a second. This clock-like cadence suggests an orderly physical process, perhaps a neutron star's rotation or orbital motion modulating the emission. Another burst in 2022 arrived with X-rays in tandem, captured simultaneously by radio and space-based telescopes, a smoking gun linking at least some bursts to magnetar activity. What began as curious anomalies in telescope data has blossomed into an entirely new field of astronomy. These fleeting cosmic sirens don't just challenge our understanding, they're reshaping it, proving the universe still holds phenomena beyond our wildest imagination. Whether natural cosmic fireworks or something even stranger, fast radio bursts remind us that every time we build a better telescope, the universe hands us a fresh set of riddles to solve. In the early 2000s, a small, unassuming device shaped like a metal cone sparked one of modern physics' most heated controversies, the M drive. Touted as a reactionless thruster that could generate thrust without propellant, it seemed to violate Newton's third law. For every action, there must be an equal and opposite reaction. The implications were staggering: a propulsion system requiring no fuel, potentially revolutionizing space travel by allowing spacecraft to accelerate indefinitely without carrying massive tanks of rocket propellant. Initial tests by engineer Roger Scheuer and later by NASA Eagleworks Laboratory reported minuscule but measurable thrust, sending shockwaves through the scientific community. The excitement stemmed from the M drive's baffling premise. By bouncing microwaves inside a sealed copper chamber, the device allegedly produced directional thrust, an effect comparable to trying to move a car by sitting inside and pushing on the dashboard. Peer-reviewed papers cautiously noted the anomaly while emphasizing the need for rigorous replication. Media outlets, however, ran wild with headlines proclaiming "warp drive possible" and "physics broken," amplifying public fascination. Crowdfunding campaigns sprouted, and aerospace companies quietly explored potential applications, despite physicists universally warning that the observed thrust likely resulted from experimental error rather than new physics. The controversy reached its peak when independent research teams attempted to replicate the results. The German Aerospace Center built an ultra-precise version in 2018, isolating the device from all possible external influences: thermal expansion, magnetic fields, even seismic vibrations. Their conclusion: no measurable thrust beyond the experiment's margin of error. Similar studies in China, Finland, and the United States yielded identical outcomes. By 2021, a comprehensive meta-analysis of every credible test confirmed the harsh truth. The M drive's thrust was an illusion, likely caused by unaccounted-for thermal effects or electromagnetic interference with measuring equipment. What makes the M drive saga so instructive isn't its failure, but how it exemplifies the self-correcting nature of science. Extraordinary claims demand extraordinary evidence, and in this case, the evidence crumbled under scrutiny. Yet the episode also revealed a cultural tension between cautious academic skepticism and public enthusiasm for frontier-breaking technologies. While physicists stressed that violating conservation of momentum would upend centuries of validated theory, many outside the field saw their skepticism as resistance to innovation. This disconnect underscores why the scientific method's gradual, iterative process, testing, falsifying, and refining remains our best tool for separating genuine breakthroughs from tantalizing mirages. The M drive's legacy endures as a cautionary tale about the perils of bypassing peer review for viral fame, but it also highlights something profound: humanity's tireless drive to question limits even when the answers disappoint. For a brief moment, the dream of propellantless thrust captivated millions, proving that our hunger to explore the cosmos remains undimmed by the laws of physics. And in that sense, the M drive's true value may lie not in what it achieved, but in the conversations it ignited about how we test the impossible, and why getting it wrong is just as vital as getting it right. Gazing into the universe's distant future reveals a haunting paradox. Our cosmos is both expanding and decaying at the same time. Current evidence points toward a slow but undeniable march toward entropy's victory, where all usable energy dissipates into an eternal, lukewarm haze, the so-called heat-death scenario. In this distant epoch, trillions of years from now, the last stars will have burned out, black holes will have evaporated through Hawking radiation, and even protons themselves may decay, leaving behind only a faint mist of subatomic particles drifting further apart every second. The temperature across all of space would approach absolute zero, making motion and chemical reactions impossible, a silent, static graveyard of what was once a vibrant universe. Yet heat death isn't the only possibility on the cosmic menu. Dark energy's mysterious influence suggests a far more dramatic finale, the Big Rip. If this repulsive force strengthens over time, it could eventually overpower every binding force in nature. First, galaxies would tear apart as expanding space overcomes gravity's grip. Then, stars and planets would be shredded when the expansion rate exceeds their structural integrity. In the final moments, even atomic nuclei would be torn asunder as the fabric of spacetime itself stretches faster than light can traverse it. The entire universe would dissolve into a soup of disconnected quarks and leptons, each particle forever isolated beyond any possible causal contact. Some theories propose cyclical alternatives, a universe that rebounds rather than fades. In these models, dark energy might decay into new matter, triggering another Big Bang in an endless cosmic cycle. String theory even suggests our universe could collide with a parallel one in a higher dimensional bulk, resetting the clock in a cataclysmic collision. Others speculate about vacuum decay, a quantum bubble of true vacuum expanding at light speed, rewriting the fundamental constants of physics in its wake and instantly transforming all matter into an alien configuration we can't begin to comprehend. What makes these scenarios so chilling isn't their inevitability, it's the timescales involved. Heat death wouldn't occur for 10 to the 100th power years, while proton decay might take 10 to the 35th years. But dark energy's behavior could accelerate the timeline dramatically. Recent measurements of supernova and galaxy clusters suggest the expansion rate is indeed increasing, though whether it will lead to a gentle fade or violent rupture remains unknown. The key lies in dark energy's equation of state, a mathematical description of how its pressure and density relate. If it crosses a critical threshold called W equals -1, the Big Rip becomes unavoidable. Despite their apocalyptic nature, these theories offer profound insights into the universe's fundamental workings. They force us to confront questions about the nature of time, entropy, and whether existence itself has an expiration date. Perhaps most remarkably, they remind us that the cosmos is far more dynamic and far stranger than our fleeting human perspective can readily grasp. Whether it ends with a whimper, a bang, or something beyond our current imagination, the universe's fate remains its greatest unsolved mystery. From the crushing embrace of neutron stars to the universe-stretching force of dark energy, we've journeyed through 30 bookmarks in nature's catalogue of extremes, each one a testament to the cosmos's capacity for both violence and wonder. These phenomena aren't just scientific curiosities. They're the punctuation marks in a grand narrative that stretches from the Big Bang's fiery dawn to the cold silence of entropy's eventual triumph. Consider the diamond rains of Neptune, where hydrocarbons surrender to pressure, or the time-stopping event horizons of black holes, where gravity rewrites the rules of reality. Even the emptiness of the Boötes void, with its galaxy-starved expanse, proves that absence can be as profound as presence when scaled to the universe's canvas. What ties these extremes together is their role as cosmic alchemists, transforming simplicity into complexity through sheer physical audacity. The same forces that forged gold in neutron-star collisions also sculpted the iron in our blood. The dark energy accelerating galaxies apart likely once propelled the inflationary epoch that made our universe habitable. Every atom heavier than helium, from the calcium in your bones to the silicon in your smartphone, was born in the crucible of stellar explosions or celestial collisions, then scattered across space to eventually coalesce into worlds and life. Carl Sagan's timeless words echo here: "We are made of star stuff, but we might expand that poetic truth. We are also the children of black holes' destructive might, the beneficiaries of dark matter's invisible scaffolding, and the witnesses to a universe that balances annihilation and creation on a knife's edge." The same pressures that vaporize planets into plasma also gently shepherd molecular clouds into newborn stars. The magnetic fields that could shred a human from 1,000 miles away also protect entire solar systems from cosmic radiation. As this cosmic tour ends, let's not just marvel at these extremes, let's recognize ourselves within them. Humanity's brief flicker of existence overlaps with a remarkable era where the universe is old enough to have forged complexity, yet young enough to still blaze with activity. We find ourselves suspended between scales, neither as small as the quantum foam nor as vast as galactic superclusters, yet capable of comprehending both. That duality, our simultaneous insignificance and uniqueness, is perhaps the most humbling lesson the cosmos offers. So the next time you gaze at the night sky, remember, you're not just looking at the universe. You're the universe looking back at itself, contemplating its own breathtaking range of possibilities.